Okay, we were looking last time about the frequency response, and we have gone through a typical circuit of MOS amplifier, and we have found out that if I use full analysis of Kirchhoff law, that is node analysis, then I can find both poles and zeros same time. But many a times, as I said, 0 is normally far away from the gain bandwidth product, that is unity gain bandwidth. So it may not be very important, and therefore one may say we may have only poles, and if those are the only poles, one among them may be earlier than the other, and the one which appears earlier, that is at lower frequency, is called the bandwidth point, or essentially the point which is the dominant pole. Okay, that is what we discussed last time. Of course there are many amplifiers. You can go into the book, you can look into the book, common source, common drain, common gate, common emitter, and all sorts of amplifiers. Please look into them. We have given a theory how to solve. Any such circuit can always be solved using the standard procedures. I will just give another method which is a very popular method in engineers, which is we discussed in some way earlier, but little more detailed circuit I may show you today. It is called zero value time constant analysis to find dominant pole. So we can actually find out dominant pole with no great difficulty. We can just do some analysis and we say okay, here is the bandwidth, because we are not interested in gain bandwidth, unity gain bandwidth point, but we are more interested in the bandwidth where the gain starts falling, okay, and that point is the dominant pole. So our assumption is the other pole is at least away, maybe one order by frequency or even 2 orders. If it is 2 orders, it is 40 dB below. So anyway that gain has no value, even if it is 10 times, it is even 20 dB down, which is large enough in fact. So essentially what we are saying, that we will be very keen to know which is the dominant pole, and our assumption to start with is that the dominant pole exists. Okay. In reality, if you do not want to agree with this, then you do full analysis and you will get all poles and zeros wherever you wish, and you can find out which is the dominant, which is the most correct and most absolutely proper method. But as I keep saying, not every proper method has to be used every time, because there is sometimes short of time of doing analysis, there is a quickness to give results, products have to be released, and on basis of experience people know this will have a dominant pole. Okay. So I am not saying this method is always valid, depends on the values of GM, Rs and everything given, it may not be the dominant which we think, but assuming there is, I have taken an example which is intentionally multi-stage amplifier, that is, it's a cascaded 2 stages of a MOS amplifier. There is a first stage and there is another stage. What I have not shown here essentially is the DC biasing part in this, okay. Though it may exist, RG may exist, and supply has to be RG1, RG2 kind, but right now only AC equivalent circuits have been, AC circuit has been shown. We also here neglect CC1, CC2 and CS bypass RE, bypass RS circuit. So there is, why we are neglecting that? Because right now we assume that they are not the part of the external circuit. This is simple analysis to show how to get it. In real life there may be CC1 here, there may be CC2 here, everywhere things will appear as they should, okay. So if I have this circuit, look at it, the first circuit can be represented by equivalently on this vein, series resistance, maybe I call it signal if you wish, I do not know what I call it, but R signal. Then there is a CGS1, CGD1, then this current source at the output, GMV1, V1 is the voltage here, which is VGS essentially. Shunting that is RO1 and RL1, which is the load provided to you. Then there is a drain to bulk voltage CDB, and this is this point. So this is my V2, okay, and somewhere here we will be my V1, okay. So V2 is now going to be the input of the next stage, okay. So this is my input, There is a CGS2 which is for the gate to source capacitance of the second stage, CGD2 which is the gate to drain capacitance between this V2 and the output. Then there is the equivalent current source which is GM2V2, GM2V2, and shunted by RA2, RL2 and CDB2. This is one equivalent, this is the other equivalent, this is one, this is other, two stage. What is the advantage of two stage amplifier per se? Why should we use two stages? Let us say I want a gain of 100. So one possibility is that I will make gain of 100 in one single amplifier. The other possibility is I may do 10-10 or 25 kind of thing, maybe 5-20 or 25 also is a decision. I will leave it to you to find out. If you cannot, next time I will tell you. If you have a cascaded stages, there is a method in which first stage gain should be higher or lower than the second stage. It should not be equal, that is definite. Whether the first stage should have a higher gain than the next stage or vice versa, on what basis we decide that. Product is 100, okay, I can make 10-10, 5-10, 5-20, 25, 33 kind of thing, many combinations I can try, 4-25, 25-4. Okay. So how do I make a choice that the first stage should have a higher gain compared to second, or first stage should have much lower gain compared to the second stage? This is something which you must find. I do not think every book would have given, but I think Sandra Smith has discussed it somewhere. Find it out. If not, I will tell you why we choose one over the other. Okay. So is this equivalent circuit clear? This is the first stage equivalent circuit, this much, and this is the second stage equivalent circuit which is given for this. What is being missed here? CC1, CS and CC2, and we shall separately handle them because we figured out those capacitance values are very high and therefore they will actually act like a short circuit at high frequencies, okay, because we are looking for a dominant pole ahead. So we are expecting that these will be short circuited at most those frequencies. However, at lower frequencies they may dominate, and we will look into them what they do when they are present, okay. So this, is that clear? What I am trying to do is to solve a two stage amplifier, MOS amplifier, and my assumption, I repeat, CC1, CC2, CS, everything is much smaller and therefore neglected at high frequency, and also RS is bypassed at that frequency because CS will be short circuited. So the bias resistance in the source also will get bypassed at high frequency. So nowhere that RS is taken care, though in real DC there will be a RS sitting there, is that clear? Shunted by CS, okay, but at high frequency RS will get shorted. Okay, having said so, as I say, this is an approximate method to estimate presence of a dominant pole, and please do not believe that every time this is true, but in most cases 99% this will be true. Okay. So you may try once a while, may fail once a while. Okay. Our assumption again is there are no dominant zeros, okay. That means 0 does not exist prior to the dominant pole. If that occurs, the gain will start rising somewhere. So our assumption right now is 0 is far away. Okay. So we say a dominant pole which is at the 3 dB point where the gain falls by 3 dB is our dominant pole P1, and again we assume that for the transfer function of the gain P1 should be less than P2 less than P3. If there are n poles, what we are saying is dominant pole is P1, next maybe P2, P3 and so on and so forth. Okay. Any transfer function of gain can be represented as numerator divided by denominator, ns divided by ds, and typically this, actually it should come here, a0 plus a1s plus a2s square nsn upon 1 plus b1s plus b2s square bnsn. This is, first look at this, then I explain this. If there are no zeros in this, as we discussed, which are dominant, the numerator part I just miss it, I say there are none coming from the numerator. What numerator will give me? 0, and I say zeros are far away, so I am not concerned about, only A0 term will remain, but that is a DC value, or that is a fixed value. So that will go into the gain, DC gain part itself, okay. Is that correct? These other terms I am neglecting, A1s, A2s square, AS, why I neglect? Because my assumption is zeros are far away, okay, far away than the poles of my query, okay. Is that okay? This is my assumption, okay, and if they are assumption, the numerator is only A0, for example. So equivalently saying, in a normal gain, voltage gain function, it can be written as some DC gain divided by 1 minus, which includes some P1 P2 value also in the product, because that when you take it out, that P1 P2 will also come outside, okay. Is that clear? This S minus P1 is actually appearing, so P1 is outside, but right now I kept like this. So everything constant is taken care in AV0. So 1 minus S by P1, 1 minus S by 2, so on and so forth. So our assumption is, if there is a dominant pole, which terms are also negligible in the denominator? S square, S cube, Sn terms will be negligible, because we said S is, first term will come from S, and we said that is the dominant pole. So we say the next terms are, so if I expand, let us say only first two terms, it will be 1 plus S times S square, A1S plus B1S square. So we say, okay, if S square terms does not exist, only the first term B1S is only dominating term. Is that clear? If I take only this product, let us say all others are much higher, even with this 1 minus something, 1 S term, 1 S square terms, okay. So which means essentially what I am going to get is something like this, 1 upon P1 plus P2, if I make product of this, but this essentially I already said P1 is smaller than P2, so even I say, okay, I neglect this, so I only say that the coefficient is essentially related to S by P1 only. Is that clear? That is what I say, the coefficient B1 here is nothing but sum of all such PIs if you take more than that, and since I's are only 1 here, so it is 1 upon, dominant pole is 1 upon P1. So how do we get this? By only observation of this transfer function, I realized that these terms can be neglected except A0. Here also other terms can be neglected. So only term which will give me dominant pole will be related to B1, and therefore that is how we can evaluate. This is the trick I am going to use. Now how do I get this P value? This is my next question. First is, we figured out that all that I have to calculate to get P1, I must somehow get, P1 is related to what in normal case? We have discussed P1, it is nothing related to other than time constants. So if there are more than one capacitors which are coming into picture, we must calculate poles occurring due to all such capacitances and the loads associated with them, okay, and then sum all of them 1 by like this, okay, and if I get that 1 upon tau average, which I am going to do, I will get my poles. Here is an example for that. Before we go this is something which we will discuss in feedback once again, but just to give you the S function which you keep drawing everywhere, it essentially has two parts. It is a complex function, sigma which is real part and j omega is the imaginary part. A plane which represents S sigma j omega is called S plane. Any function, complex function can be represented on sigma j omega. I think this is maths you must have done by now n times, okay, this is just to show you. And if the poles are real, okay, real, then they and minus, then they must lie on the left top plane. Sigma must be 0 for them, but the imaginary, j omega term must be but only real values. If there are only real poles available, then all should lie on the left top plane. And which is the dominant one which will occur earliest? So P1, P2, P3, Pn poles will be shown here. Is that clear? So let us say where 0 can occur, 0 can occur here, maybe we will say 0, and in that case it is on the right half plane, and then system may become unstable as we shall see here. So we will prefer 0 to occur somewhere here on the imaginary axis, or even if possible it is on the left half plane, even safer, or it actually sits on the P1. Is that correct? I can do that. I can actually adjust the value of this 0 either here or anywhere, so that the system becomes more stable, and we will see this little more detail when we come to stability. Any zero or poles on the right half plane actually leads to instability. What does that mean? That the gain starts increasing and not decreasing, is that correct? And if increasing means it keeps increasing, infinite means system will go to VDD, power supply maximum voltage, so it will start saturating out, so it will not remain amplifier, so we say it become unstable, is that clear? So we want to see the system remains amplifier. So what is the trick I am keep on telling you all the time, that please remember amplifier is the only system in the analog circuit which is of relevance. Everything else is derivable from this, okay. All that we keep saying is, if I know my amplifier design, I know almost everything, because all are only derived part out of it, because the theory which I will use for amplifier designs is as much required for oscillator designs or A to D converter, anything which I do later, this is good enough for me if I know my amplifier theory properly. That is why I am spending so much of a time on this, otherwise I would have actually said, okay, read this, you are done in 12th or maybe in first year, but I want to make it very clear that why we are spending so much time on amplifiers, because once we understand how do we get amplifier designs, then we know roughly everything in analog, okay. So if I take an amplitude of this, it will be dominant pole for this will be AB01 plus omega 0, and Bode plot is correct as long as omega is less than P1. Till that time gain is constant, beyond we do not know whether dominant poles where they occur. So what I am saying, if I dominant, this is my pole P1, up to this at least, okay, I know gain is constant. From here onwards, and then I do not know, excess other poles may further start falling it down, minus 20 further and further, okay. But I am interested in where it falls first, okay, which is called the bandwidth. Why it is called bandwidth? The term bandwidth was given up to which gain is constant, okay. So that value is of our interest, okay. Can we tailor P1 as well? Yes, I can, as I said other day. If I put a 0 here per se, what will happen to there? Till the next pole occurs, which then will become dominant, the gain may become higher. But something else I have given by that, and just check, just we will see what happens in feedback, we will use this theory. Oh, I nullified that, but I lost something else, okay. I increased bandwidth definitely, okay. Is that clear? So something I must be losing in getting higher bandwidth, okay. So we will see what exactly we lost, is that okay? We will see that little later. So is that issue clear? So this plane has been shown to you that I must get my real plane, real poles on the left half, that is minus value they must occur, so that the system is stable, otherwise it will be a growing system, and we do not want system to grow outputs inadvertently, okay. So this part, as I said, this figure is just shown here, we will come back this figure again. Okay, so the method which I suggest, which is called zero value, not I suggest, is given in many other books, I did not see very much in the this book, Cedar Smith book, and therefore I thought I will write down for you. Okay. In zero value time constant assay, what we see, every capacitor sees some equivalent resistor, sees, now that word sees is very important. And then we say, and if that resistance, equivalent resistance is Req, the time constant associated with that capacitor is Req times C, is that correct? So if you have as many capacitors you have, find R equivalent for as seen by each of them. Now the analysis which we did is something interesting here. Our assumption here is superposition theorem is valid. What does that mean? That is, the influence of each capacitor is independent, which may not be in reality many times, is that correct? The capacitance with CGD may influence both all sides in fact, but our assumption is each capacitor is independently controlling outputs to input ratios, and therefore if we can take independent influences of all capacitor and we add all of them as their time constants, then we say average value is okay. Okay, this is our assumption. superposition theorem is what we are going to apply. What is the, when superposition theorem is true? When the system is linear, then only superposition is possible. And I repeat, I did tell you once, if not we check again, y is equal to mx plus c is a straight line, okay. So looks to be linear, it looks like a linear, but it is not a linear system, is that correct? Y is equal to mx plus c is not a linear system, but which is linear there? Y is equal to mx is linear, but y is equal to mx plus c is not a linear system. So don't think that if a straight line occurs, it is a linear system, okay. What does superposition say? If x change to 2x, y should also become 2y, okay, and only then superposition is valid in this case. So okay, this is assumptions, since we are making n assumptions, n plus 1, okay. So if there are n capacitors, we say tau 1 is R equivalent 1 C1, tau 2 is R equivalent C2, tau n is this, and then we say the net tau is just sum of all such taus, then the dominant pole will be 1 upon tau average. This is what we are going to say, okay. Now let us see in our circuit, which we just now put, please have this. How many capacitors you are seeing? One is CGS1, other is CGD1, CDB, CGS2, CG2 and CDB. There are 6 capacitances which are of relevance, 1, 2, 3, 1, 2, 3, okay. So we like to see each capacitor sees how much equivalent resistor, is that correct? And if I get that equivalent resistor, I get RC time constant for each of these capacitance, and then I sum all those time constant, and 1 upon tau is the dominant pole. Now why I am saying this method, the first day when I solved something a MOS amplifier and I gave you a dominant pole expressions, please verify whether the expression I get from here is same as what I got there, okay, and you will find to your great surprise it is almost same, if not exactly same, almost same, okay. So let us see that almost same part is how almost. So the first capacitance of interest is CGD1. Which one I talk? CGD1. I am talking of this circuit, CGD1, okay. Is that okay? This is V2, this is this. So whenever I will do this analysis, the first thing I will do is short all independent sources. Open the current source and short voltage source, okay. Short all voltage sources, independent, please remember the word independent. Short all independent voltage sources or open all independent current sources. If I do this, okay, then at the V1 I get only RS, please look at that circuit, since VN is 0, so only RS remains, this is the voltage V1, okay. Then there is a CGD1, a capacitance here, at the output GMV1 plus RL dash, and now we assume that the next stage is right now removed as if equivalently, that is equivalent input for that is shorted, removed from this, okay. So we say the output is VO1, which is RL1 dash is RL1 plus RC parallel. If your RL is high, you can say RL dash is RL1, that is fair enough. Now the condition which I am going to say, replace this capacitor by a current source I. Replace this capacitor by a current source I. Is that correct? And we say the drop across the capacitor is plus minus V. Is that clear? V across the capacitor, the voltage is V plus minus V. Is that okay? Then we say the resistance seen by the capacitor is V by I. Is that clear? Method I repeat. Replace the capacitors by voltage V, calling this call as V plus, plus minus V, and a current source of I connecting that. Is that correct? So what is the, is that every capacitor I will replace it by current source V and drop that across is V. Is that clear? This is what the zero time constant analysis is, what we are going to do, okay. I shorted V in, I replace the capacitors by equivalent current source I, which gives you a drop of V. then the V by I is nothing but the resistance seen by the capacitance. Okay. Now if that is so, yes, why we removed? Oh yeah, we say loaded is unloaded case, okay, because we are doing superposition, we only take care of each individual efforts. The other capacitance I will short out, okay. So the other loads as if are not, no output, input is going to the output side, equivalently say, okay, that is what we did, okay. The assumption is superposition theorem is valid in what cases and why we can sum off each component time constants has nothing to do with time constant per se. Any function can be such way added and average can be taken. This is a theory, mass theory. We just have applied it to our case to get equivalent values of that, okay. It is a functional system, I am just applying it to a circuit system, okay. Is that okay? Now if I do this, you see, keep seeing your circuit. What is the drop across RS? V1. What is the drop across RS? V1. So I times RS is V1, okay. If you look at, please look at this circuit, if you, I do not know whether you can get, maybe or thoda le le, okay. Now thoda sa dekh. So the drop across RS is V1, IRS is the drop which is V1, but if you see the other side, this is I minus GM V1, remember I is in this direction, so the current passing in RL dash is minus I and minus GM, both are currents opposite. Please remember this is the actual current direction to get VO1, is that correct? How do I get a voltage drop? IR, this is the current side, but actual currents are both opposite sign. So minus I minus GM V1 into RL1 dash is nothing but V0, 1 or called V2. Yeah, please ask. Current direction is in this direction, I, यहाँ लिखा है ना एरो I, ये भी opposite है इसके, ये भी इसका उल्टा जाएगा ऐसा, ये भी आएगा ना, ये ऐसा जाएगा, है ना, और वोल्टेज कैसे नापते हैं? Like this. So VO1 is essentially minus I minus GM, some of them actually with a minus sign, into RL1 dash is VO1. However, what is resistance associated? V is how much? Voltage drop across capacitor is how much? V1 minus VO1, okay, divided by I is the resistance, So if I substitute from here in this, I will get minus I1 plus GM1 IRS into RL is V0, and then take V0 by I is this, V1 by I is RS from here. So I write V1 minus V0 1 if you keep calling. Then RGDO1, this is the name I give you, CGD 01 is the capacitance, the resistance seen by CGD1 is RGDO1 which is RS plus RL dash plus GM1 RS RL1 dash. Is that okay? Just sum, there is nothing, just get the terms correctly, okay. So have I got which resistance I got? Resistance associated with CGD1. I can do same analysis for every capacitor, is that correct? And if I do this, I can get correspondingly R equivalents for each of them, okay. Is that point clear? I have shown you one. Every time you must do that circuit, draw that and see if there is no current source, GM term will go away from there, okay. Okay. So having shown this, similarly if I say RGDO2 is seen by CGD2, then RGDO2 will be RL1 dash. Why this RL1 dash is coming here? What is that RL1 dash? Essentially equivalently the RS for the next stage, okay. So RL1 dash plus RL2 dash into GM2 RL1 dash RL2 dash. So this is the resistance seen by CGD2, that is second stage feedback capacitance, CGD2, okay. It is identical stage, is that correct? The first stage and second stage, only thing is RS is replaced by RL1 dash, because the RL1 dash acts like a source resistance for the next stage. Okay. Similarly then I can see RGSO1 is seen by CGS1. RGSO1 is, how much is RGSO1? You can see in the circuit. How much is this is seeing? You short this RS, only resistance it will see is RS. So I said okay, if I that so, then RGSO1 is RS, RGSO2 is RL1 dash, which is the RS for the next stage. How much is RDBO1 this capacitance is seeing? Parallel combination of RL1 and RL2, because the next stages are short, all capacitance are removed. So only resistance seen is this much, okay, RO parallel RL1. So if I do that, this is RDBO1 is RL1 dash, by same argument RDBO2 is RL2 dash as seen by CDB2. So have I now calculated equivalent resistance seen by all 6 capacitors? Is that okay? So what is the method I am suggesting? See for each of this, only the case which will occur whenever the GM terms on the V other terms occur, then you will get this longer expression, otherwise only simple resistances will appear. Only in those cases you will get RL plus RS plus GM RL RS kind of term, rest of the time it is straightforward. Okay. So I calculate all equivalent resistances seen by capacitance. So I can calculate 6 time constants. Is that clear? RC, RC, RC for all of them. Is that okay? So if I do that, then I see RGSO1 is TGS1, TGS2 is RGSO2, CGS2, CGD1, RGDO1, CGD1. Only thing, this is long enough, because you can say that is the only place where the value is large enough. CGD2 is this, CDB1 is this, CDB2 is this, and then by our assumption of zero value transfer function theory, one can say average tau or sum of the tau, net tau is sum of all this tau, okay, and the dominant pole is 1 upon tau, okay. So is this method clear to you, to everyone? What is the method I suggest? Take every capacitor, find equivalent resistance seen by it, take RCs of all of them, sum of that 1 upon tau is your pole, dominant pole, okay. Now we will, maybe not today, next time I will give one problem and show you that, yeah, you solve fully and you solve with this, the values are very close to each other and therefore valid in the example I will take, okay. Please see, I am repeatedly telling you the circuit solving which last time I showed, putting all nodes, all capacitances, solve everything using nodal equation is the ideal solutions. Is that clear? Nothing can go wrong in that, because we are not missing any term anywhere, okay. So if you solve nodal equations for full equivalent circuit, that is the ideal situation. But many times I know that I am not interested in any other parameter than the bandwidth, I can even resort to this technique and can get the solution faster. Is that clear? Like first day I showed you, if you only use dominant poles, then what is the problem we got? Zero आपके हाथ से निकल गया, okay. Then we say नहीं, then how do I? So in this assumption, why that zero is not relevant? If that is relevant, this theory still is not valid, okay. But in most cases, it will happen that 0 will go beyond GBW, that is gain bandwidth, 1 dB gain bandwidth, 1 dB frequency, it will always go beyond that. So in most cases, unless of course you tailor for the other one, change it, this will not occur, okay. And therefore the solutions are normally okay, but not necessarily every case is correct. Okay, so having shown you the tricks which many of us play in actual designs, so I am trying to keep saying you all that if you are only doing analysis, do correct analysis. Why stop it? Is that correct? I mean, you have a circuit, you draw equivalent, solve it. If you are going through a SPICE, it doesn't require any approximation. Let it put everything there ना, उसको करने दो ना, आपको तो करना ही नहीं है. Let it solve any difficult problem. Okay. But if I had to solve numerically, समझ से कितना होगा? then I don't know, I say okay time constant roughly kitna hai, itne seconds hai, microseconds hai, nanoseconds hai, or itna bandwidth hai iska. So that is the way designers in the lab do, or in the chip design we say okay roughly I require this, so should I put W by L so much because this GM will help me, okay, and that is how I keep adjusting value when because remember SPICE, which is an excellent circuit solver, it requires input file from your side, okay, that means you will have to give that inputs, okay. Now if there are variations, how many variations you will try, 100, 1000, million? So somewhere at least where to start at least should be known to you, okay. Even if you are going on a SPICE, the first guess has to be relatively okay, okay, even if you are doing a full circuit analysis using SPICE, okay. So otherwise what will happen, you will put some inputs and you will get some output which will always, SPICE will always solve that IGV, it cannot stop you otherwise. But what is the values of G's and I's, V's you have put, it depends on you which currents it will show, okay. Therefore how many things to be within control you should use is this techniques show you, is that that's why we keep telling you how on a SPICE, it's not arbitrary, you have to decide how much to, otherwise many of my graduate students say, oh sir a whole night I was working. So what was he working, he gave some wrong guesses, whole night music सुनता रहा, SPICE तो चलता ही रहा, उसको तो आप कुछ कर नहीं सकते, वो he is taking step by step and trying to solve it, finally he said it gave a correct solution after say 23 hours, so 23 hours I worked, you didn't do anything actually, okay, because you were foolish to start with the wronger inputs and now you are just doing this repeatedly, changing dx, someday it will come finally. So you have to understand that even using a simulators, you ought to be academically sound enough to give correct inputs. Otherwise, the time conversions will never occur, okay, and therefore solutions will never seen by you. So people always say, sir, हमारे पास SPICE है, we can always do. Yeah, you can do it, and you will do it in 10 years, okay. But tomorrow I need the result, okay. So what do I do? So these theories which we keep telling you, the methods we are suggesting are even using SPICE, you should know. Otherwise you say everything is doable now. No, it's not doable. Okay, let's do something different before we quit this amplifier frequency business. Last time we said in all so far analysis that this so called coupling capacitor, the shunting capacitor across RS are neglected by us. Okay, and we solved everything just for high frequency, and all that high frequency they were all treated short circuits, okay. But at frequencies very low, small enough, their impedances are not infinites or shorts, zeros or whatever it is, they are effective then. But at those frequencies the other capacitors may not be working, CGD of if omega is very low, then that impedance will be infinite. So the capacitances which were very dominant at high frequency may not be dominant at lower frequency. The capacitance which will have impedances dominating at lower frequency will be not dominating at higher frequency. So this is the value system which allows us to separate the two. If they are very close by, then this may not be correct, then we must take all of them together, but this does not occur. CC1 will be of the order of microfarads. How much was CGD1 and this value last time in the class I said? Puff. So I am talking of the order of 10 to the power 6, that is 6 order higher or lower values are chosen for the other two. So these capacitance, this may be even 20 microfarad or 30 microfarads. You have done this exam, I think you must have already done in a lab, how much the electrolyte capacitor you have to put across the RE or RS, okay, very high values. Okay, this is also a small query which in the lab someone should ask, why electrolyte capacitors cannot be, their polarity cannot be changed, okay. By all other capacitors you can connect both ways, okay, but electrolyte capacitors need to be connected as given plus minus. Why? What will happen? Of course they will rupture, that I can tell you, try once and it will burst also, okay. But why those otherwise all capacitances are directionless, I mean you can put this way or that way. So why electrolyte capacitors behave little differently, okay, they are polarity dependent, okay. So let's look the effect CC1, CS and CC2, and which capacitance are now I am neglecting, CGS, CGD and CDB. I said, oh, these are not relevant for me. This is AC ground. Why did I put AC ground? VDD for AC is ground. So this is AC ground. This is the AC equivalent I am showing you with a transistor on. This is my bias capacitance RG, this is R signal, this is CC1, this is RL, this is RD, and of course there is a RS I should show here, okay. Now I figure out, let's look at the only input side, this side. How much is VG? It's a divider. This voltage, this impedance or resistance divided by the net impedance, is that correct? Into Vn is Vg. So Vg is Rg upon Rg plus R signal plus impedance due to capacitance, is that clear? Which is 1 upon SCC1. Look at this part, in Rg1 parallel Rg2, but that is same as equivalent Rg, because the other terminal will go to the AC ground. Rg once the second terminal is also going to the AC ground, that is ground. Rg2 is also, other terminal is going to the ground. So both are in parallel anyway, so they are equivalent, okay. So this Vg is Vn. I can do little readjustment of the term, that is what I say, first multiplied by SSC1 across this, put SC1 above, then take Rg S1 outside as I did and readjust the terms. So I get Rg upon Rg plus R signal into S upon S plus 1 upon CC1 into Rg plus R signal into V. Same expressions can be converted into this expression. What is this value? DC, because DC means zero frequency, do not say DC per se, that is frequency independent term, okay. That is like AV0 kind, equivalently saying. This is S upon S plus omega. क्या होता है ये ट्रांसफर फंक्शन, किसका होता है? अभी पहले 1 अपॉन एस प्लस ओमेगा होता तो कौन सा फिल्टर होता? लो पास, फॉल होता ना, लो पास, एक पोल आया इसके आगे ब्लॉक कर देगा वो, ये कौन सा होगा? इट्स ए हाई पास फिल्टर, ओके, इट्स ए ट्रांसफर फंक्शन फॉर ए हाई पास फिल्टर. सो राइट एट द स्टार्ट CC1 is giving you high pass filter, is that correct? This has to be understood that this is giving, so certain up to certain frequency it may not pass, but beyond that frequency it will pass, is that correct? That means below this particular frequency the gain may fall, the input may fall, or that is Vg will be very small or negligible. Beyond that only full Vg will be made available to you. This is the trick we want to utilize, okay. Please take it, if you read the books, it is not identical to what I say there, but still you read book much more seriously, because they give many more details than what I give, okay. But what I teach here is only that, how they will look into it, okay. What I say essentially is I actually tell you something in between the lines, okay, and book gives all the lines. So don't miss lines or don't miss in between the lines, okay. So I am only complementing what is given in the book, I am not replicating what book gives. Please remember, I am not replicating all of it, I am only telling you what is they meant by that. Clearly V0 by Vn is a transfer function which is some constant into S upon S omega 0, which is the transfer function for a high pass filter, okay. So ये थ्योरी बताया कि जैसा ही आप ऐसा देखते हैं एसेंशियली, तो बोडे प्लॉट में कैसा दिखना चाहिए आपको? हाउ डू यू एक्सपेक्ट द बोडे प्लॉट टू स्टार्ट? इफ आई प्लॉट, ऐसा गेन दिखाया मैंने और ये ओमेगा है, कैसे कहां से शुरू होना चाहिए? हाई पास है, यानी क्या होगा, इधर तो हाई पास है और इधर क्या होगा, फॉल होना शुरू हो जाएगा, तभी आपको हाई पास बोला ना आपने, and this is our pole where it starts becoming constant. Okay, so abhi what we are going to see now, that each, there are how many capacitances we have? 3. This is our mid band gain. So the 3 capacitances must, say for example, something 3 poles must appear due to 3 capacitances, and each will actually give rise value 20 dB, 40 dB and 60 dB to reach this mid band value. Is that clear? To reach this mid band value, and beyond this what will happen? Gain will become constant. So this frequency is what, let us say this, the frequency at which mid band starts, and this is our first pole. So this is called FL, this is called FH, and what is the bandwidth really? Bandwidth is defined where gain is constant. Normally FLs are very small compared to FH. FLs are very small compared to FH. So FH, many times we call the FH itself as the bandwidth. It's something like telling this is 1 megahertz and this is say 1 kilohertz. Okay. So you subtract 1000 minus 1, 999 kilohertz, which is as much as 1 megahertz. Is that clear? So many times we do not define bandwidth by FH minus FL, we may say FH itself. But if FL is not very small, as we thought here, let us say it is 100 kilohertz, it is reducing substantially. So I must understand what is the value of FL before my assumption that the bandwidth is only FH, or otherwise calculate FL and subtract from FH. Independently, numerically it may get subtracted or not, is not your choice. We just subtract. Numerically if it is very small, it will not be worth 6 decimal, or if it is equivalent, it will reduce the number in first decimal. Okay. So you have to understand that we must evaluate every time, and numerically values sometimes may not be worth actually subtracting. Okay. But we must know what is the low value itself. Okay. So where from these low values are coming, therefore CC1, CC2 and CS, these are the capacitances being very high, they will start dominating at low frequency. Is that clear? So first thing, we want to now calculate the effect of CC1, CC2, see this. So CC1 का तो आपको pole दिखा दिया मैंने. Which is the pole for CC1? CC1 sorry, this RS RG है, sorry. Let me write again. The first pole which I am seeing is RG plus R signal into CC1. A first pole आने वाला है. Maybe we call it omega P1 for the sake of it. Now we don't know whether omega P1 is the first or second or third. We will see values and we will accordingly say which one is 1, 2, 3. But right now we call 1. RK, for example, this figure, this is the value which we are talking. As? Oh, S is the numerator. R, essentially it says that at there is a 0 at 0 itself. That means beyond that the gain is rising anyway. When S is 0, means that omega equal to 0, the 0 occurs, what it tells that the 20 dB plus it should start at right from the ahead. But this other value, lower one, is a pole which is also now increasing because of the S upon term, which essentially you say you divide by this, your equivalent value if you calculate, it is still rising, okay, equivalently. This is reducing but this is rising, okay, so the average is still rising for you, okay, average is still rising for you. That is why it is called high pass. As you rise, it's then at S is equal to infinity, it will become constant, which is equal to this. You can see what I am saying, it is 1 plus omega 0 by S. If this becomes infinite or very high, this will become constant, okay. No, I am only saying that this is what transfer function of high pass filter is. S upon S plus omega is a high pass filter. Okay, we will do filters again and we will show you why it is high pass. Actually we will evaluate that value. Okay, Right now you assume 1 upon S plus omega 0 is a low pass filter, S upon S plus omega 0 is a high pass filter, okay. At lower frequencies RS is not bypass, this fact has to be understood, but at higher frequency RS is bypass. So this, in calculation of low frequency RS cannot be neglected because RS is used for DC. So RS is actually coming there, is that correct? This is only bypass when frequencies are very high, otherwise RS appears because this impedance is not shorting RS, this is finite. The capacitance due to CS 1 upon omega CS is comparable with RS, so RS cannot be neglected, but if that is equivalent to 0 then we say RS is shorted, is that clear? So at low frequency RS must be considered. At low frequency CS is not shorting, at high frequency CS shorts and therefore RS shorts across. हाँ वो जो अभी मेथड दिखाया था ना टाइम कांस्टेंट, उसके लिए अब मैं बार बार नया फिगर नहीं बनाना इसलिए वहां लगा के रख दिया मैंने। आपको अभी मेथड बताया ना, कैपेसिटर देखो कितना आर देखता है वो। ओके, इफ दैट सो I just done for one of the capacitance, rest you try yourself. I take a case of say CC2 which is at the output side. Please look at the circuit again. For this capacitance, this is the RL and this is the RD. Input is shorted, corresponding with this goes. So we say CC2 sees V1 minus V2 RD and RL. So how much is R equivalent for that? I just done the maths. V1 is IRD, V2 is minus IRL, V1 minus V2 by V by RD plus RL. So what is the equivalent resistance seen by CC2? RD plus RL. So tau CC2 is RCC2 times CCC2, which will give me the another pole which is 1 upon 2 pi RC2 CC2. I have done analysis for all three, but I am showing you the final result. Try methods I suggested. Then the poles occurring due to the CS capacitance shorting RS or across RS can be given as GM by CS. Solve the same method as I suggested. Okay, GM by CS. Okay. ये GM क्यों आ रहा है वहाँ पर? Can you think why it is coming? Please look at it. This current is passing through RS. We have done common source with source resistance, same method I am using. This current is passing through. So this voltage is this drop plus this drop, and that is why that GM term is appearing. Okay, please look back what we did earlier. Okay, so the another pole which I see due to CS is GM by CS. Okay, how much will be CC1? क्या CC1 देखेगा? सेम मेथड से बोलो, आपके फिगर में बोलो कितना होगा? RG plus R signal, that's the only resistance it will see. These methods are not so very common in the books. Of course you can go and now read the book, either of four of them whichever I gave. They have little more rigorous, or maybe they are putting some arrows, looked into it, is a GM equivalent this. Finally what they will get is what I am getting without doing all that. Okay, that's the way I do it. Is that fun clear? You solve complete circuit, everything comes. You don't have to do any of my methods. But I always show you plus something which is otherwise known to others. Okay, ठीक है, ये मेरा नया method है. Okay, if that's so, last part we write. Okay, this also is done. Finally, if we see, there are three poles, omega P1 due to CC1, omega P2 due to CS, and omega P3 C. This, since we know roughly the values, we figure out omega P1 occurs here, omega P2 occurs here, omega P3 occurs here. This is the Bode's plot. You will say why it will be, it can be omega 3 also, whichever comes. Okay, but by general knowledge of the values, GMs we use, RGs we use, R signal we use, you can see why this is the lowest. Can you think? देखो जरा फंक्शन में क्यों वो सबसे लोएस्ट लग रहा है आपको, RG is very high na, so obviously that will come first. Okay. Then between the two also, because the CC2s are very high, okay, this will actually come this it will come the last. But anyway, this may change once a while because GM value is decided by the current I bias, okay, and that may change some values. But as of now, because CS is even higher, this will start down. Please remember CS is relatively very high. Shorting the RS, the capacitance are 30 microfarad, 25 microfarads. So GM by CS will be earlier than omega P3. But if happens to be, then call this omega P3 and call omega, don't tell me sir आपने इधर बोला, ऐसा नहीं, value जो भी हो. But since I know CS are very high, they of course are not as high as RGs, therefore first will come this, then it will come this, and then it will. This is 20, this is 40, this is 60. Okay, you are perfect. He is right. Essentially what we are saying, that once you rise, the second pole spills over and then it also gives another 20 dB. Because it's a pole, it must decrease. Essentially what we say, it's a pole means it will decrease. 60 का 40 हो जाएगा, 40 का 20 हो जाएगा. Is that clear? It's a minus 20 dB pole दे रहा है, तो 60 ऊपर से चला, फिर 20 नीचे आया, 40 हुआ, फिर और 20 नीचे आया, तो 20 हो गया. Is that okay? And then it reaches, so what is FL here? Which value is FL? Omega P3 is the 1 upon 2 pi, FL is omega P3. So I got my lowest cutoff frequency which I can evaluate and say okay, this is the FL. FH, how do I calculate? By my dominant pole theory I get my FH, and FH minus FL is the bandwidth. Please remember in amplifier which two parameters are of interest to us? The gain and the bandwidth. So we evaluated both of them. Okay. What is the third one which is also worrying us? Please share. Phase, but somehow you are assuming stable, phase is less than 180. Yeah, you are perfect. Phase margin as it is called. But what else? There is another term which is worrying us, which we never so far calculated. In every system, that first we must calculate. What is that? Power. The most worrisome part in all of this, at the end of the way we find, it is the power dissipation which will limit, okay, everything, okay. Okay, there is a sentence which I said someday to you, I don't know. Design a low power amplifier. When I say power amplifier, I want higher power, isn't it? That's what I meant by power amplifier. Otherwise, voltage amplifier normal ho jayega na, ya current amplifier. So I say power amplifier. Then I said, no, you please design a low power amplifier. What do I mean? What did I mean that time? The dissipation should be very low in the devices or the circuit, but the delivered power to the load should be as high as possible. Is that correct? So that is why it's called low power amplifier, because you need large power to be delivered, but you don't want the circuit to dissipate larger power. Okay, so sometimes this fun is made low power amplifier, so it's essentially meant this. Okay, okay, so this finishes all kinds of normal amplifiers, single stage. Others which I have not done, please read: common source, common gate, common emitter, emitter follower. All of them are given in book. Method is identical to all of them. Okay. The most important of all these amplifiers are not really single-ended amplifiers. Okay, which amplifier we use maximum? You already started working on it. Which amplifier chip you are using? Op-amp. So is the op-amp is essentially different from all that we did? Yeah, it is somewhat different, but it follows much of the laws which we discussed in single-ended amplifier. So that amplifier, op-amp has 3 stages, maybe n stages also one can do. A typical op-amp will have first block as we shall call diff-amp, differential amplifier. Okay, Then I'll put it second stage, we will say gain stage. And finally, a typical op amp has 3 stages: differential amplifier, followed by a gain stage, followed by a buffer stage. Okay. So any op amp you see only, how do you see all of this? You only see this. Of course this plus minus is relevant, but iske, of course there is a bias points they also show here, plus VDD minus VSS. This is your V in some way connected and this is your VO. So op amp essentially contains, a good op amp at least should have around 22 transistors. Okay. अभी तक के एम्पलीफायर में कितने ट्रांजिस्टर लग रहे थे, 1 2 ऐसा ना, तो op amp में 22 ट्रांजिस्टर हैं. So it is not a real simple looking things, but individually if you see, it's not very difficult. Okay, it's not very difficult. So let's look from which stage I should start with before I go for op amp. No, diff amp. First stage in the op amp is diff amp. So let's see diff amp. The word diff amp essentially is called differential amplifier. Okay. There is also a word difference amplifier which is not same as differential amplifier. Please take it. There is a word which we will use called difference amplifier, though it is similar but not same. So do not make same names. Difference amplifiers and differential amplifiers are different as far as their outputs are concerned. The architecture may not be very different. Okay, so please take this in your mind. Sometimes someone very casually uses, so I thought I should explain you. There are 2 kinds of diff amp in the market, op amps in the market, one using BJTs. Which ones you are using? The numbers right now, 741, which is mostly bipolar. Okay, 741C is a MOS device. Okay, so either you can get MOS op amp or MOS diff amp, or you can get BJT diff amps. All differential amplifiers have 2 inputs, V in 1 and V in 2. Okay. Then we define two signals for any differential amplifier. Okay. One we call difference signal. What we call is difference signal, which is called VID. I stand for input, D for difference. Is that correct? VID, ID are subscripts, V is the voltage ID. So VID means input difference voltage, which is subtraction of the 2 inputs V in 1 minus V in 2. Okay. So what signs VID can have? VID can have which signs? Both or one? Both, because V in 1 can be larger than V in 2 or V in 2 can be larger than V in 1. If you define V in 1 minus V in 2 as VID, it can be either plus or minus. Is that okay? Plus minus. VID can be plus minus depending on which one is higher or lower. Okay. We define another signal which is called common mode signal, called VCM, common mode, okay, which is nothing but the average of the 2, V in 1 plus V in 2 by 2. These are the 2 input signals we will use in all our differential amplifier theory. Okay. Now first thing first, why are we so keen about diff amp? Abhi tak all amplifiers we have seen, we can have a gain of any stage by cascading or by cascoding. Okay. By cascode I can also fool people by not losing bandwidth but getting the gain higher. So why I am interested in differential amplifier? So here is some big advantage which differential amplifier gives over all single ended amplifiers. Major advantage of DFAM is it has a much higher immunity to environmental noise. Okay, that means if the noise is, please remember in a normal single ended amplifier at the input if noise comes, what will happen at the output? Noise will also get amplified by the amplifier along with the signal. So पहले तो आपके पास मिलीवोल्ट माइक्रोवोल्ट नॉइज आया और बाद में मिलीवोल्ट नॉइज आ गया. ओके, तो सेकंड स्टेज में आने तक तो नॉइज ही नॉइज दिखा आपको, है ना. So if you use single ended amplifier, noise cannot be eliminated. Of course I should not say that word because we do try that also. But as of now we say normal common stage, cascade or cascade stage, noise is enhancing every gain stage because that also sees the same gain. Okay. So DFAM has the biggest advantage that it eliminates so called this noise. Okay. That is what we are looking for. Why we are looking for reduction in noise? Because we want signal to be amplified and not noise. What is the term we use for this? Signal to be amplified higher than the noise, then what is the ratio we look for? Signal to noise ratio. So what we are really looking for any amplifier is large signal to noise ratio, SNR as it is called, SNR, signal to noise ratio. Okay. So all amplifiers should show higher signal to noise ratio. Single ended amplifiers do not do that, okay, because their SNRs are maintained. Same noise also get enhanced. I want to improve SNR. Okay. So how do I do it? The differential amplifier improves SNR. That's what it is all for. Okay. It also allows you higher voltage swings than the single. Why? What do you mean by higher voltage swing? As a larger signals, larger swing of signals, what happens in a single ended amplifier? What will happen if the input signal is very high? We kept saying on day one, small signal, small signal. If signal is higher, what will happen? Saturation means harmonics will start coming, other frequency component will also come into picture, it will start saturating. Compared to single ended, this can give larger swings. Okay, that's the trick of the trade. एक्चुअली वो लार्ज नहीं है, एक क्या एक तरफ ऐसा है और उसका उल्टा इधर रखा है तो एक तरह ऐसा लगता है कि स्विंग ज्यादा है, थोड़ा फूलिंग है, बट है. बट देयर इज ओनली वन डिसएडवांटेज. हाउ मेनी ट्रांजिस्टर्स सिंगल एंडेड विल रिक्वायर? वन ट्रांजिस्टर. ओके, हियर द मिनिमम रिक्वायरमेंट इज 3 ट्रांजिस्टर्स और मोर, एज आई से आई शो यू. ओके, एटलीस्ट 3 तो लगेंगे, बहुत भी लग सकते हैं. As I said, total number of devices required on a op-amp are 22 minimum. Okay, so और भी लग सकते हैं. So there is an additional area penalty on the chip if you are making a chip of an analog block. Okay. Otherwise, DFAM is very good, very good. And its difference gain, as we shall see, is extremely high. How much? Anyone? Typically difference amplifier or differential amplifier has a large open circuit gain is very high, 10 to the power 4 or 10 to the power 5. How much is normal gain of an amplifier? 10, 20, 100, 1000, maximum 600, 700. I can go to 10 to the power 5. Okay, that's the biggest advantage DFAM will provide. Very large gains it can create in open circuit system. We'll see what that word means. I have 2 single-ended amplifiers, M1 related to this, M2 related to this. Is that clear? I have 2 single-ended amplifiers, have a common power supply voltage, drains are common. The only thing is now I am saying I am substituting inputs Vin1 and Vin2 to the 2 amplifiers and I am picking up 2 output voltage VO1 and VO2. But what I am going to do, if individually this amplifier I have to solve, I can solve. Individually if I have to solve, I can solve. But what I will be interested in, what is Vin1 minus Vin2 amplification to VO1 minus VO2. Ratio of what I am looking for? Output difference. VO1 minus VO2 is the output difference divided by input difference. Vin1 minus Vin2. What is that value? That is where the difference amplifier is differential. Is that correct? Is that point clear? The difference of input and difference of output. Okay. I can also say one of the output divided by difference input, that also I can look into. Is that clear? That is VO2 divided by V in 1 minus V in 2, or VO1 divided by V in 1 minus V in 2 also can be of interest. These devices these are called single ended outputs, when only one of the output is of interest to us. Okay. Both will be present, but only one is of interest to us. So we will see both of them. If I do this and these are, then I have to do independent biasing for both of them. Is that clear? Because these are two amplifiers, I will require bias for both of them. Let us say I put a current source here, current source here. So I need two current sources to bias independently, and they may not be identical any time. Is that clear? So I said, okay, why not I join the source of the two transistor and connect a common current source. Is that word clear to you? Here if I put it, I will require one current source here, one current source here. Okay. They may not be identical in many cases, may be identical, but I need two sources. So what I did, I merged them and put one common source, common current source. Okay. What is current source doing? The biasing the two transistors. Is that clear? Biasing the two, and where should they get biased? What is the state of these two transistors? Should be all the time saturation. They must remain in saturation. If they come out of saturation, they will not amplify. This will go to linear modes then, okay, or cutoff modes. So they must remain in saturation. That's our condition for amplification. Right now they can be different, but in most cases, if you are in a single silicon chip, RD1 will be equal to RD2. So if you go in the lab, you pick up these two separate amplifier and connect, these two may not be identical. Even if you, let us say you chose a 47 kilo ohms resistor, two 47 kilo ohm resistor do not have 47 kilo ohm exact values. Some may have 47.15, some may have 46.9, though they are marked as 47K. So RD1 may not be identical to externally. If you put two devices, they may, but if I make on a single chip small area, I can more likely say RDs will be equal. Okay. So is that point now getting clear to you? Why op amps are not made by making simple separate MOS transistors and hooked up on a board? Is that point clear to you? Because nothing can be then made. M1 cannot be same as M2 in a two separate transistors. You buy, okay, M2 or M1 they can never be identical. उसका VT same नहीं होगा, उसके sizes same नहीं होंगे, okay, GM same नहीं आएगा. But on a single chip where there is one less than 10 micron square area, I can almost ensure that both transistors are identical, both have same threshold, the resistance values are same. So all the time such circuits will be always integrated circuits and not discrete circuits. Is that clear? Because discrete circuit will lose all its advantage. Okay. So all op amps will be always ICs and not made. Though there is an experiment I have set up in 90s, I think it continued for a while, I don't know now. I purchased some MOS arrays, okay. That means on a single chip more than one transistors, maybe each has available source drain to you. Use those arrays and then create, because since on a single area all those transistors were made, they will have almost identical properties. So there is a MOS arrays through which you can try making an op amp or at least def amp in your lab, and you say it may come closer to what you are looking for. No guarantee that still it will be good, but at least it will come closer to this. Where on a single chip everything is acceptable, RDs will be same, these two transistors will be identical. Okay. How much non-ideality, non-identical term you can tolerate is another, this is called variability issue. Some other time we will discuss that. Variability also is an issue, but not here. If I see its input output characteristics, why we are interested in doing all this, if I plot Vn1 minus, that is V difference versus V out, which is VO2 minus VO1 is shown here, but individually if I plot V out 2 and VO1, I figure out the V out 1 will follow this curve and V out 2 follow with this curve, and somewhere here both will cross halfway. This is very important point. V out 1 ऐसा आएगा, एक ऊपर से नीचे माइनस तक जाएगा या कम वैल्यू में जाएगा और ये उल्टा हो जाएगा. What does that means? M1 M2 are कॉम्प्लीमेंट्री. एक ऊपर गया तो दूसरा नीचे आता है, दूसरा ऊपर गया तो पहला नीचे आएगा. So this is the trick which DFAM is playing. Is that correct? Because I connected their sources and I am now applying V in 1, V in 2, change in V in 1, V2 will switch over which transistor will start conducting, okay, and because of that I will get, and because if I subtract V out 1 minus V out 2 and plot VID, the typical curve will be like this. What is this range should be called? This is the linear range, that is the plus minus VID. This is the only plus minus VID acceptable for DFAM for which gain is linear. What will happen to here? It is constant, okay. Constant means what? Zero gain or high gain? Zero gain, no change in output but change in input. So gains are zero. So only in this range DFAM will operate. Is that correct? Because gain is changing, dV by dVn is changing. Is that correct? Here it is 0, here it is 0. So this is essentially the, okay, this word is very important. This is called input range, okay, up to which DFAM will operate. We will show you this later. Before I quit, last minute, I just said in DFAM the noise is eliminated. That is what I said you. You can see V in 1 and V in 2 will have same noise because they are close by same area. So whatever noise appears here will also appear here. Is that clear? And now we will see noise does not come because of the source, noise comes from the environment. Is that clear? Noise comes from the systems. एक तो EMI बोलते हैं, इंटरफेरेंस है, दूसरे रेजिस्टेंस है जो केबल लाते हैं वहाँ से, वो सबके लिए सेम होते हैं, okay. So generally the environmental noises are identical in a small area. If you say this area, yeah, even there the noise, my voice is noisy, let's say, and you are not shouting, so your noise is zero there. So it's a differential, but in chip the noise will be almost same for both. Okay, it's like overreading. Whatever is true, it will overread on both sides, both inputs. Okay, and then the gain which I am looking, which we say V in 1 plus V in 2 by 2, and if the noise is same, what is the common mode value? Will be same as one of the noise, and the output will become 0. That's what I am going to say. So what will happen? Noise will get eliminated at the output. This is exactly what I am looking in a DFAM, that common mode signal should not get amplification, but different signal should get amplified. So common means which ones? Noise is common, so that will get eliminated. Signals are different voltages, yeah, they will get amplified. Therefore a DFAM has advantage that it improves the gain of a different signal but actually removes the common mode signals. Is that clear? That is the advantage of differential amplifiers. See you then.